Welcome back. This is the second lecture in a three-part series for the day. Hopefully it won't be as long as the last lecture, and I'll probably give you a little bit longer after this next lecture finishes, before the next lecture starts, because watching videos for an hour and a half and taking notes and all that fun jazz, I know that's your life goal. But just bear with me and take a break. But I'll try to give you more than 5 minutes next time. All right, so in our last video, we defined KVL and KCl. Okay, KVL states that the number of voltages in a loop, which this is loop dependent, a number of voltages in a loop always sum to 0. KCl says that the number of currents traveling through a node sums to 0. So currents through nodes, voltages through loops. Okay, and since voltage and current are inherently linked, KVL and KCl work together to help define an entire system. Okay, so really that brings about an interesting point. Most of what we do in this class, in fact, nearly all of the math we're going to do in this class, I'm going to exclude digital circuits for this point, all of the math we're going to do in this class is founded on the following formulas. I'm going to give you every formula we're going to use for the first part of the semester. Okay? You're going to want to write these down. You're going to want to keep these in a safe place. This is going to be your cheat sheet. When you go to the exam, you're going to need to know these formulas. They're all going to be helpful. Okay? So, every formula we're going to use for analog circuits, everything that has to do with power, everything. I'm giving it to you all day 2, lecture 5. All right, equation 1. We have KVL, sum of voltages in a loop equals 0, okay? And then we can just say sum of voltages in a loop is equal to 0. We have KCl, sum of currents through a node equals 0. Or we can write it as in equals out, so I'm going to go ahead and do that. In equals I out. All right, there's 2 equations knocked down. Now, these 2 equations work well with, we know our equation for power. Power, P equals VI. That's another good equation. Our equation for energy, E, I'm just writing the word E because it's, why not, is equal to the integral of power, derivative of time. Oop, don't know why I put a parenthesis on there. Or this could be similar on the other side of it, where power is equal to the time derivative of energy. Okay, this is also going to be true. Okay, and now we have these 2, which are system equations. We have these 2, which are component type equations. And then down here, we have 3 equations that connect voltage and current through a component. Okay, so these are system equations, these are power equations, and then we have our component equations. In a resistor, the relationship between current and voltage is linear. It's called Ohm's law. You should all know that one. You should all have had that handed to you. And the equation for that is V equals IR. Voltage is equal to current multiplied by resistance. Or on the other side, I equals V over R. Current is equal to voltage divided by resistance. inside of a resistor, this is true. This is only true inside of a resistor. This is not true in a capacitor. This is not true in a battery. Capacitor does not have a linear relationship between voltage and current. In a capacitor, the current IC is equal to, well, I guess I should say VR, IR, VR. That's the voltage across the resistor is equal to the current through the resistor multiplied by the resistance. The current through the resistor is equal to the voltage across the resistor divided by the resistance. Okay, here the current through a capacitor is equal to, and that's an I. I like drawing lowercase letters for this reason because uppercase letters don't always carry well. I is equal to the time derivative. Oh, I should say. Sorry. Is equal to C, which is the capacitance. Capacitance is like resistance except for it's specific to a capacitor, times the time derivative of the voltage across that capacitor with time. And that is current. If we want to write it on the other side, VC is equal to 1 over C times the integral of IC dt. All right? And then for an inductor, the relationship between current and voltage is flipped. Here the relationship between current and voltage is that current is the time derivative of voltage. In an inductor, it's the opposite. Voltage is the time derivative of the current. So here, VL is equal to L, where that's the inductance measure, measured in henries, DIL dt. Okay, very similar equations, opposite ends of the spectrum there. And then on this side, VL is equal to 1 over L times the, nope, IL, my bad, times VL dt. These are all the equations we're going to use for the first half of the semester. This is all analog systems. This is everything you need to know. You're welcome. So why are we going to show up for the rest of the semester? Because some of these equations have derivatives in them, and if we're going to combine these with this, which we will often, what we're going to find out is that we're going to have second order systems, and it's going to require differential equations. So that is what we're going to be covering for the rest of the semester. Diff EQ, we're going to start right now, yeah! No. We're starting with resistance only circuits because this relationship is linear. This is pretty. This is less pretty. Combining these two is even less pretty. So that's fantastic. But now that I've given you every single formula that we're going to use in this class for the rest of the first half of the semester, digital circuits is much simpler than analog circuits. If you ask me, the math doesn't involve integrals. Now that I've given you this, write all of this down. Have this someplace accessible because you will use all of these on the exam and probably more. But every one of these formulas is valuable and will be used in this class. If you have a question about when I used a formula, it always comes back here because I gave you all of these formulas. These are experimentally derived or definitions. The definition of power is voltage times current based on the definition of voltage and the definition of current. Okay. Similarly, definition of energy is the integral of power based on the definition of energy and the definition of power. Okay. These were all experimentally derived. These are based on the conservation of mass and the conservation of energy. So all of these formulas came from somewhere. I helped derive these two in class, kind of theoretically to the high order. There was not a lot of math. These I'm just giving to you. We're not going to use these two for a few weeks. we're going to use this one a whole heck of a lot starting next week. But there you go. Every equation we're going to use for the first half of this semester. And all of the hardest equations you're going to need to know for this class. And everything else is a derivation of those. Whoa! Suddenly got all like very blurry. Apparently I showed my butt or something and the camera was like, ah! No! No butts! Alright, I'm going to give you a system. A very simple system. Power supply, some kind of a component. It could be a resistor, could be a capacitor, could be an inductor. Okay? This is going to be V source is equal to plus 12 volts. Alright? And let's say that when we do our calculations through the system, we find that the current coming out of the source is equal to 0.1 amp. Okay? Now, before we start anything, KVL requires loops. KCL requires nodes. What we're going to do before we do anything is we're going to establish where we want our nodes to be and where we want our loops to be. Now, I'm going to put a node here. Now, remember, a node is any section of wire that doesn't have an electrical component on it. So as long as I can draw a straight line of wire without touching, well, without going through a component, we can call it a node. So if I were to put a node here, this node and this node are the same. Now I can make them different nodes if I want to. That's not going to hurt anything. This can be node 1, node 2. But they're both at the same voltage. And I already know that. Okay? And that's not going to hurt anything. So here, I'm going to put a node here just for funsies. This is going to be node 1, this is going to be node 2. Now I know that there's one wire going into node 1, and there's one wire going out of node 1. There's one wire going into node 2, there's one wire going out of node 2. Easy peasy. Now I'm also going to draw a loop. A loop is a continuous line that I could draw by which an electron could travel and reach its original destination. Okay, and I could draw an original line that goes here, down here, like this. I'm going to represent it around the inside by doing this. And I'm going to go ahead and call this loop 1. That's an L. Okay, so we have loop 1, node 2. I've got that already set up. I am ready to do KVL, KCL. Okay? So, our KVL equations. Now, the number of equations that you have for KVL are dependent on the number of loops in your system. How many loops do we have in the system? Well, we have 1. It's loop 1. It's not that exciting. So, for loop 1, we know that the number of voltages in this system, I'm going to go ahead and say that this is R1. We know that the number of voltages in the system equals 0. So we know Vs plus VR1 is equal to 0. We know that to be true. Now, conventions for KVL. This is kind of an important thing to note. Your power generating members, that being batteries, or you may have a transformer that brings power into a system, any kind of power source. These are bringing power into the system from something external. Okay, in a battery, it's coming from a chemical reaction. In a voltage supply, it may be coming from a wall socket. In a transformer, it may be coming from another inductor. Regardless, any power generating members are negative. Okay, so when we go to plug this in to this loop equation for Vs, it says positive 12 volts. It does increase it by 12 volts. It's brought in here as a negative. You could put it where all of your power generating members are on the right side and all the power consuming members are on the left side. That's fine. Now, either way, you end up with the same equation. It equals 0. Okay? So you could say VR1 is equal to Vs, well, a positive version of Vs, which ends up being a positive 12. So negative Vs comes in as a negative, it's a negative, it's a negative of a negative. That equals a positive 12 volts. So we know that the voltage drop across R1 has to be 12 volts. It has to. At this time instant, with this voltage, an electron traveling through the system is going to lose 12 volts, gain 12 volts, lose 12 volts, gain 12 volts, lose 12 volts, gain 12 volts. Always going to be cycling between 12 and 0. That's not really all that exciting, but it's foundational. Okay, so that's all we can do for KVL. For KCL, we have two equations because we have two nodes. So at node 1, now we have one value that's coming in, one value that's coming out. I'm going to go ahead and say that R1 has a voltage change of VR1 and a current value of IR1. That's the current traveling through component number 1. Okay? Regardless of what it is, this could be a resistor, this could be a capacitor, this could be an inductor. This relationship doesn't matter. This is always going to be true. KVL and KCL are always true regardless of what component it is. Okay, so at number 1, we know that the current coming in, which the current coming into node number 1 is IS. So we know IN equals I out, IN is equal to IS, I out is equal to IR1. So we know IS is equal to IR1, and that's true because of KCL at node 1. So what that means is we know IS is equal to 0.1 amp, so 0.1 is equal to IR1. Ta-ta-ta! That was pretty simple. Okay, and then we can do this equation at node number 2. At node number 2, our IN is equal to our I out. Now we know the current is flowing in this direction, so our IN to node number 2 is IR1. Our I out of node number 2 is IS, because IS is going in that direction and IR1 is going in this direction. IR1 goes into 2, IS goes out of 2. So we know that, once again, IR1 is equal to 0.1 amp. That's pretty simple. That's KVL and KCL in a very simple circuit. Okay. Now it does get a little bit more complex the more we decide to push the boundaries here. So yes, heck yeah, we're gonna push boundaries. Very simple solution. Let's go to a much more complex one now. Same principles apply. The same concepts apply. The same formulas apply. Also, the camera always goes blurry whenever I show my butt. It's rude of me to show my butt. It's weird. Every time one of your teachers teaches a class, a lot of the time they spent showing you their backside, like while talking to a whiteboard. It's weird. I'm trying to teach this whiteboard knowledge. You're going to learn. All right, new system. In this new system, I'm going to use resistors. You could use any component. Okay, now you got a VS. We'll say VS is equal to 10 volts. And we'll say that we've done the math on this system and we've calculated IS is equal to 2 amps. Okay? Great. This is going to be R1. This will be R2. This will be R3. This will be R4. And this will be R5. Okay. Now at R1, R1 experiences a voltage drop of VR1 and a current traveling through it of IR1. VR2 experiences a voltage drop of VR2 and a current value of IR2. And that's the same for all of these. There's nothing spectacular about saying that each one of these has both a current and a voltage applied to it. Okay, we don't know what VR1, IR1 is for most of these components yet until, hot dog, we do math. Those three component equations that I gave you, resistance, capacitance, inductance, the relationships between current and voltage in each of those components, they do apply. Here, in each one of these, because I drew them as resistors, what is true for each one of them is that V, R, whatever the component is, I, is equal to I, R, whatever the component is, times R, I, whatever the resistance is of that component. Okay? And that's true for all 5 of these resistors. VR1 equals IR1 times R1. VR2 equals IR2 times R2. VR3 equals IR3 times R3. I don't need to say the rest of them. I'm tired. It's friggin' 9 o'clock in the morning. I'm not even supposed to be awake. Ugh. It's terrible. No, but seriously, over break, I did, like, not wake up at 9. It's fantastic. Got so much sleep, I didn't know what to do with myself. I giggled myself all day. But we know that component relationship is true. So if we knew what R, I, or V was for any one of these components, we would be able to figure out what V or I is. Basically, you only need 2 to figure out the third. And using a combination of 2 of those, finding out the third, then plugging it into KVL and KCL, we know what everything is. Okay? So, similar to the last round, what I did at the very beginning was I established nodes and loops. This is going to be node 1, 2, I guess I could make this 3 if I really wanted to. Sure, why not? 4, and then I'll make this 5. Okay? Now you'll notice that I can draw a line that connects 2 and 3, and there are no components touching 2 or 3. So what that means is I know they're going to be at the same voltage level. Now there is a little bit different of a value when it comes to current. We know that the current going from 2 to 3 is equal to the current going from 3 to 4, because that's 1 in, 1 out. So the current going from 2 to 3 is equal to IR3. We know that to be true. But let's play with math. Math time. I need to have a catchy math time song. It's math time. Oh, dang, I said catchy, and then that was not catchy. It's like a 1990s jingle. It's math time. Now prepare yourselves for a rigorous mathing. We're all gonna mathetize together. Okay, nobody ever hired me as somebody to tell them about math jingles, okay? At least not yet. It'll happen, just wait. Also, most people didn't expect me to come up with math jingles on the spot. Oh. Alright, let's play with KVL and KCL. Oh, right. Before that, I have to establish loops. I'm going to create this loop. It's going to go along the interior here. We'll call this loop 1. I'm going to have a second loop. It'll go along this out here. I'm going to call that L2. Okay? I'm going to have a third loop that goes along this part here. I'm going to call that L3. And then I'm going to have a fourth loop that just goes around the very outside. And we call that L4. Okay? So a total of 4 loops. Inside, here, here, and then there. Okay? 4 different ways I can draw loops. Now, according to KVL, you can actually create this as a loop. You have to count one of the components as negative because you're counting the reverse. So I could create a loop number 5 that just goes inside of that pane. It's loop 5. You can create a loop number 6 that just goes inside of this pane and call it loop 6. I can do that. Math is a little uglier, but I'm going to include that just for the sake of showing you, and then I'm going to tell you don't do that. Okay? Usually you need to include a power generating element in, otherwise the math becomes weird. So let's start with KVL, because I did all that beautiful work deriving those loops. In loop 1, what we know from loop 1 is loop 1, an electron travels through R1, R2, and R4. And then goes back through the source voltage, okay? So we know that V R1 plus V R2 plus V R4 is equal to Vs. And where Vs is positive rather than negative. Okay? That's one equation. Next equation, loop 2. We know VR1, well, an electron goes through VR1, VR3, VR4, and Vs. So we know VR1 plus VR3 plus VR4 equals Vs. Now I can tell you right now, just looking at these two equations, VR2 has to be equal to VR3. Why? Because everything else in this equation is the same. VR1 plus VR4, no, Vs, if I were to zoop, Vs minus VR1 minus VR4 equals VR2. Well, that same value, Vs minus VR1 minus VR4 equals VR3, okay? Which this is equal to that, so we know that these two have to be VR2 equals VR3. I can tell that just by looking at those two equations. Now, if we go to loop 6, it'll prove that VR1 equals VR3, but VR2 equals VR3, but we're not there yet. Okay? So, loop 3. In loop 3, we go this direction. Okay? So, here we know VR1 plus VR2 plus VR5 is equal to Vs. Okay, that's pretty neat. Now, I could take these two equations right here and figure out right away that VR5 is equal to VR4. Why? Because everything else is the same. VR1 plus VR2 plus VR4 or VR5 is equal to Vs. Vs minus VR1 minus VR2 is equal to VR5, which is also equal to VR4. Therefore, VR4 is equal to VR5. Just taking these two equations, combining them, you can prove that to yourself. I'm not going to write that again, but I know that for a fact. In loop number 5, which is the loop I told you not to do, you can go ahead and prove that to yourself. And I'm going to write it out there because I like to prove it, but whatever. Loop number 4. Now loop number 4, the electron goes around the outside here. So we have, it goes across VR1, it goes across VR3, it goes across VR5, and then it goes back to the source, okay? Once again, I can take these two equations and show that VR4 equals VR5. Why? Because again, you cover these two up, the other three components are the same. Prove it to yourself, whatever. Now I'm going to go ahead and take loop 5. Now loop 5, we have an electron going here, traveling this way, coming back here. Now we know when it's going this way, it's actually traveling against the current of R4. And for that reason, because we know that the current going through the R4 is pointed, it's pointed downhill towards the source voltage. Because of that, when we write out loop 5, what we have to do is say negative VR4 plus, because when you come back here, you're traveling with the direction of the current. You know the current is going this way through R5. You know the current is going this way through R4. We're going against when we force that electron through this loop. So this one has to be a negative. We're going with when we bring the electron through this loop. VR5 is equal to 0 because there is no source voltage in that loop. It's just a constant loop like this. This is true. Now, when you solve this equation, you find that VR4 equals VR5. Okay, we already proved that to ourselves by combining these two equations or these two equations. But this equation is redundant, but it is a valid loop. Okay, now L6, we have to say the same thing. Okay, in L6, we're just doing this loop. Now we're forcing an electron to go up against the grain. We know that IR2 goes this way. So when we plug this in, this becomes negative VR2 plus VR3 equals 0. Now when we plug this equation in, we find that VR2 equals VR3. We found that by combining these two equations. So joy of all joys. That's awesome. You can also combine these two equations and find the same thing. VR2 equals VR3. That is proven through loop 6. But again, this whole entire equation we already knew. This is nothing new to us. I would not advise you to write down your loops that don't include the power source element. It does make things a little bit more ugly. But it is a valid loop. But you do have to put in that negative sign in order to make this work. If you forget the negative sign, VR2 equals negative VR3, what does that mean? It means like one of them is like gaining voltage? Like no, it means you're going against the grain when you write the equation. You're going against the flow, the natural flow of current. Okay, so those are our KVL equations for this circuit. Okay, and we can, if we know what VR1, VR2 is, we can solve for VR5. We know what VR5 is, we know what VR4 is. Okay, if we know what VR2 is, we know what VR3 is. And we've solved our entire system that way. Just plugging in those equations will give you whatever you need. Now, let's do KCL. At KCL, we have 1, 2, 3, 4, 5 nodes. And I've already told you, that node 2 and 3 are basically the same. But you know what? Whatever. We'll keep it in there for now just to prove a point. So first equation, at 1, we have one wire going in, we have one wire going out. The wire going in is the voltage, the current that comes from 5 to 1. So I'm going to go ahead and write that as I5 to 1. That's current coming in. Current going out is the current going from node 1 to node 2. Current going from 1 to 2. Now, it's a little bit of a confusing way to do it, but I know the current going from 1 to 2 is equal to the current going through R1, right? Because current coming from here and going through here has to go through R1, which means that is the current I R1. Now the current going from 5 to 1 is IS, and that's a positive value because that's the direction the current is going. So I5 to 1 is equal to IS. So here, if we just replace I5 to 1, current going from node 5 to node 1 with IS, if we do that, that's valid. IS is equal to IR1. That makes sense. The amount of current coming in is coming from the source voltage and going through resistance 1. So we know IS is equal to IR1. We already know what IS is. So if we use our relationship, we know what IR1 is now. If we know what R1 is, we know what the resistance R1 is. We have IR1, we have R1, we can calculate what VR1 is immediately. Just using KCL and the equation that we know, we have two values needed to solve that resistance. We're good. Once you have two, you can figure out the third. Yeah! Heck yeah! All right, so at node number 2, we have one current coming in. It's the current coming from 1 to 2. So I1 to 2. We have two currents going out. One from 2 to 4. I2 to 4. And then we also have a current going from I2 to 3. I2 to 3. Okay. Now because we have a node voltage there, a node there, the current going through here, we're not going to assume that's the same. Let's go ahead and figure out I1 to 2 is the current going through component R1. So this becomes IR1. Okay, we already know what IR1 is because it's IS. IR1 is equal to the current going from 2 to 4. That is the current going through R2. IR2 plus I2 to 3. Well, at this point, we don't know how much current is going there. So I'm just going to leave this as I2 to 3 because we don't really know that. Now, at 3, we have I2 to 3 coming in, and then we have I3 to 4 going out. Okay, now we know that I3 to 4 goes through component R3, which means it's going to be equal to IR3. So I2 to 3 is equal to IR3, which we could have figured that out already. So, but now we can take this and we can bring it and plug this in up here, and we find that IR1 is equal to IR2 plus IR3. Now, if we were to just write this equation and not have node 3, I1 to 2 equals I2 to 4, okay, and ignore the fact that we have a node 3, when we write out I2 to 4, we would have to write out that there are two branches. There are two output branches that go from 2 to 4, and those two output branches are IR2 and IR3. When we get to 4 to 5, I'll show you that again. All right. But including 3, it does make the math a little uglier. It's unnecessary, and having nodes where your nodes are merged, it makes the equations a lot simpler because you don't have to go back through it and plug things in again. Okay, so let's go to 4. At 4, we know that the current coming in, it's coming in from two branches. Okay, it's coming in from I2 to 4 and I3 to 4. Okay, two branches. And it's going out through two branches, but it's going out to the same node. Equals I4 to 5. Okay, and we'll have to remember this is two branches. Two branches going to the same node. I2 to 4, that's only one branch. I3 to 4, that's only one branch. If you prefer to write it this way, go ahead. I2 to 4 is equal to IR2. I3 to 4 is equal to IR3. Now this is two branches again. That is equal to IR5 plus IR4. Okay, we know this is true because of the junction at 4. The two currents coming in equals the two currents coming out. All right, and then we have one more node, 5. At 5, we know that the two branches coming into 5 is equal to the one branch going out. So the two branches coming in happen to both be IR4, I4 to 5 is equal to I5 to 1. Okay, I4 to 5, there are two branches connecting 4 to 5. That includes the current going through R4 and the current going through R5. Both of those branches converge here so that when we draw a circle around here, we have one coming out, excuse me, and we have two coming in. The two coming in both come from the same node, but ultimately come through two different components. So this will be represented by two different components. The one coming out goes to one component. So we'll represent it with one component. So I4 to 5, you have IR5 and IR4. So IR4 plus IR5 is equal to I5 to 1. Here goes through one component is the same as IS. Okay, and those are all of the equations That one doesn't really help us. But those are all the equations that we would need to solve different currents in the system. These are the physical restrictions on each of these currents because of the law of conservation of mass. KVL equations gave us the restrictions on the system based on the law of conservation of energy. KCl gives us restrictions on the system based on the law of conservation of mass. Okay? So those two equations together should be able to give us ultimately what it is we need to solve this system. In combination with all the equations that come out of KVL and KCl, plus the component constitutive equations, resistance, capacitance, and inductance, with those three equations, plus maybe power and energy equations, we can solve this entire system. We can figure out what every single voltage and every single current is everywhere. We're going to do that next week. Oh, that's a threat. All right. Let's go ahead and take a 10-minute break. We'll take a 10-minute break this time. I will see you at 9:40. Yeah. I'll see you at 9:40, and then we'll have a 30-minute class. I'm going to discuss Raspberry Pi stuff. I think there was one thing else I needed to discuss too. Hope I think about it. So I will see you back here at 9:40. I guess it's a little bit more than a 10-minute break, but I'll see you back soon. Those of you who are watching this not live, I will see you right away as soon as you click on that video. Or I guess I won't see you unless I'm staring through your webcams, which I'm not. I haven't reached that creep level yet. All right, take a little break.